We've talked a lot about solving equations in the past, and when we solve an equation, we use the principle whatever we do to one side, we do to the other, because that keeps our equation in balance. The question now is, how does it work when you have two sides that are not balanced, when you have an inequality, an inequation? So what I'm going to do here is just go through a number of scenarios, and I have a starting statement here. 2 is less than 4, which we know is true. And what I'm going to do is different things to both sides, and then look to see if the new statement is still true. So let's take our 2 greater than 4, and let's begin by, to both sides, I'm going to add 2. So I'm going to add 2 to both sides of this. That would become 4. That would become 6. And my question now is 4 less than 6 still. Is that still a true statement? It is. I added 2 to both sides. I got a new statement, and that new statement was still true. All right, let's try subtracting. 2 is less than 4 is our starting statement. I'm taking 2 off of both sides, so that would be 0, and that would be 2, and there's my sign. I've got a new statement. Is it true or false? Is 0 less than 2? Yes, it's true. Let's take another scenario. Let's take our statement 2 less than 4. Let's multiply both sides by 2. The left side would become 4. The right side would become 8. There's my sign put in. Is that still a true statement? 4 is less than 8. All right. So far it seems that if I do the same thing to both sides, the inequality remains true. In other words, the side that was largest to begin with is still the largest. Let's keep going though. 2 is less than 4. Divide both sides by 2 on my original statement. I get 1. And 2 is 1 less than 2. Yes, it is. It's true. Next scenario. Let's multiply both sides by negative 2. So the left side would become negative 4. The right side would become negative 8. And is negative 4 less than negative 8? It's not. It's false. All right, so that's the first time that's happened. Let's try dividing both sides by negative 2. The left side would become negative 1. The right side would become negative 2. Is negative 1 less than negative 2? Again, it's false. All right, so we have a situation happening in which it seems if we multiply or divide by a negative, we get a new statement that is not true unless we reverse the sign. So I've written this out. It says, from the above, it is clear that if we multiply or divide a true inequality by a negative value, multiply or divide by a negative value on both sides, then the new statement is no longer true. And since we want to keep statements true, what we're going to do is, to make our new statement true, we're going to need to reverse the direction of the inequality sign. In other words, to make these statements true, if I'm going to multiply both sides by negative 2, I'm going to have to reverse the sign to make the statement true. Okay? And that's a key principle in solving inequalities. So let's solve a few inequalities applying this principle. We want to solve the inequality here over the set of numbers indicated, and we want to graph our solution on the number line. And I go ahead and I solve it the same way I solved equations, just keeping in mind that if I ever multiply or divide both sides by a negative number, I'm going to have to reverse the sign to keep my statement true. So to isolate x here, I'm going to have to add 1 to both sides. And we know from what we talked about before, if you add a number to both sides, the new statement, here comes the new statement is still true. So I leave my sign the way it was. The next thing I need to do is multiply both sides of the equation by 2 to isolate. And if I multiply both sides by a positive number, as shown in my previous discussion, I know that the new statement, here it comes, remains true. And I don't need to reverse the sign to keep it true. So there's my solution. Any x value greater than 12 will make my original statement true, as long as x is a natural number. So I want the natural numbers that are greater than 12. All right, so natural numbers again are 1, 2, 3, 4, 5, the counting numbers. Alright, so the first thing you would think about it would be 12. Let's put 12 on the number line. But if I put 12 into my statement here, 12 is not greater than 12, so it is not part of my solution. So the first number that is would be 13, then 14, 15, 16, etc. And we'll just put that to show its pattern is continuing in that way. If I want to check my work, I take any of these numbers. Let's just take 16 and check it. If I put 16 back into my original statement, I would have 16 divided by 2, which is 8, minus 1, which is 7. And I can see that 7 is greater than 5. It satisfies my inequation. In number 2, I have the exact same question as I had above. The only difference is I have x as a set of real numbers. So my solution would all solve out to the same thing. I'm not going to resolve it. X is greater than 12. But as a reminder, real numbers are all numbers, decimals, fractions, whole numbers. So when I go to plotting my solution on the number line, 12, 13, 14, I want all the numbers to the right. But I don't want 12 because 12 is not greater than 12. 12 is greater than or equal to, but there's no equal sign there. So remember, I put an open circle to represent that. And I'm showing my solution as a statement and pictorially as a number line. Let's do one more example. We want to solve this inequality over the set of real numbers. So to isolate for x, I'm going to subtract 4 on both sides. Keep in mind, we're doing inequalities. The sign may switch if we do a certain operation. We've subtracted 4 from both sides. Subtracting from both sides keeps the statement true without reversing the sign. So there we're down to that. The next thing we're going to do is we're going to divide both sides by -2. Alright, and so here's where flags should go up. I'm about to divide both sides by -2, which means that my new statement will be x on the left, -3 on the right. But since I'm dividing by a negative, to keep the statement true, I need to reverse the sign. And the sign would be that. Alright? So let's graph our solution and then we'll check to make sure that it satisfies our original inequality. So I need some numbers around -3, smaller numbers off to the left, bigger numbers to the right. And I now want to highlight numbers that make this statement true. So -3 is less than or equal to. It makes this statement true. So I'm going to color in -3. And then I want other numbers that are less than or equal to -3, which would be all the numbers off to the left. So I can color them in. Anything in the highlighted region should make the original statement true. So let's take a number in my shaded region. Let's take, for example, -4. It's in the shaded section, so if I substitute that in here, I should get a true statement. Let's work it out down here. So -2 times -4, which is my test number. So far that's 8 plus 4. That would make the left side 12 and the right side is 10. Yes, that's a true statement. And so my solution looks correct.